Hello everyone, this is Surojit and you are welcome to our channel. Well, in last two lectures, we have learned spherical symmetric charge distribution and cylindrical symmetric charge distribution, as well as we also learned how to calculate electric field for these symmetric charge distributions using Gauss law. Now in this video, we'll quickly cover plane symmetric charge distribution. So first we'll see what type of charge distribution is called plane symmetric charge distribution, and we'll also learn how to calculate electric field for this plane symmetric charge distribution. Well, as we have noticed for spherical symmetric as well as cylindrical symmetric charge distribution, first of all, for spherical symmetric charge should be distributed over the spherical region, and for cylindrical symmetric charge should be distributed over the cylindrical region of infinite length. Similarly, for plane symmetric charge distribution, first of all, this charge should be distributed over an infinite plane. So what is the first condition for plane symmetric charge distribution? Charge should be distributed over an infinite plane. Okay, so this is the first condition. And then second condition, let's consider a point on this plane, and then around this point, if we draw a circle, concentric circle on this plane of different radius, and if we measure the charge density at every point on this circle, and if we get the same charge density at each point on this circle, then only we can say this charge distribution as plane symmetric. Now the charge density will be same on each circle, every point on this circle, when the charge density will be uniform. That means if the charge density is everywhere on this plane is constant, then only you will see the charge density on this circle, on this circle will be same. But if the charge density depends on coordinate system, then you will see at different circle, on this circle, they have different radius. If the charge density depends on coordinate system, then on each circle you will see the different charge density. Okay. But in order to be a plane symmetric charge distribution, the charge density is supposed to be constant, same on the each circles, and that is only possible when the charge density will be uniform. Uniform means it will be independent of coordinate system. Let's say sigma equals to sigma naught, constant everywhere. Everywhere. So second important point, that charge must be uniform over the plane. Charge must be uniform on the plane. On the plane. So if any charge distribution satisfy these two conditions simultaneously, then we can say this charge distribution as plane symmetric. This charge distribution as plane symmetric. First condition, charge should be distributed over an infinite plane. So in this case, this plane is infinite plane, and the charge density must be uniform. Charge density must be uniform because why this charge density must be uniform? You see, in order to be a plane symmetric, if we draw a circle of different radius around this point, concentric circle, the charge density on each circle must be same. And when the charge density on each circle must be same, only when the charge density on this plane at every point is uniform, then only the charge density on the circle will be same. If it is non-uniform, then you see at different point on the circle, at different points charge density will be different. So also this charge distribution will not have any plane symmetry. So this charge distributions will have only plane symmetric only. This charge distributions will have plane symmetric only when say uniform charge density. Uniform charge density, and if this charge is distributed over infinite plane. Okay. Okay, so now we have understood what type of charge distributions is called a plane symmetric charge distribution. So let's now what we want to do, we want to calculate electric field because of this type of plane symmetric charge distribution using Gauss law. Okay. So before calculations electric field, we have to check two important points. First important point, what will be the directions of electric field above this plane and below this plane? And second, as we have noticed for spherical symmetric or cylindrical symmetric, whenever we have used a Gauss law to calculate electric field, the first step we have to consider, we have always drawn a Gaussian surface, and through which we can actually calculate the flux easily without doing any difficult integration. So same thing here also, we have to learn how we can draw a Gaussian surface for plane symmetric charge distribution. And not only we have to draw the Gaussian surface, we have to draw a Gaussian surface. Keep that in mind that we can easily calculate the flux through this Gaussian surface without doing any difficult integration. Okay, so we'll check these two important points. So first important point, what will be the directions of electric field above the plane and below the plane? For that, let me just remove this circle lines from here, and also impose me a coordinate system on this plane. Let's say this is XY plane, and this is Z axis, and this is Y axis, and this is X axis. Okay, so this is Z equals to 0 plane, that's mean XY plane, and in this case X and Y, let's say varies from minus infinity to plus infinity, and charge density is sigma equals to sigma naught, so independent of X and Y. So and Z also. So this plane is infinite and charge density is uniform. So this charge has plane symmetric. Now what we want to see, what will be the directions of electric field because of this symmetric charge distribution. So in this case, what will be the directions of electric field above the plane and below the plane? Above the plane and below the plane. So for that, let me just consider a point P on the Z axis. P on the Z axis, and then if we consider a portion, infinite portion, which is parallel to the x-axis and thickness, let's say dy, and at a distance y from the x-axis. So now since this plane is uniformly charged, so these portions will behave like as a infinitely charged carrying wire, and if we calculate electric field because of this wire, what we'll see, the electric field because of this wire at point P will be along this direction. Electric field will be along this direction. Now since this plane is symmetric, I mean it is uniform plane, so it will be symmetric around about the x-axis and y-axis, because the plane is first of all, this plane is infinitely long, and this plane is carrying actually uniform charge density, so it is symmetric about x-axis and y-axis. So because of that, we can consider another identical portion like this on the other side of the x-axis, that is at y equals to minus y. So this point is y equals to minus y, and this portion will also carry the same charge distribution on it. Whatever this portion is carrying, both the portion will carry the same charge distribution. So now if we calculate electric field because of this one, second wire at point P, the electric field will be along this direction. Electric field along this direction. Now see, for both the wire, this distance and this distance are same, and this distance is also same. So because of that, we can say this distance and this distance will also be same, and these angle are also same. In this case, from this figure, you can see this angle are also same. So because of that, if we decompose this to electric field, so before that, let's say since this distance and this distance are same, and both the wire carries the same charge on it, so they will create a electric field at point P with equal magnitude. Now since these two angles are same, so if we decompose these electric fields into two orthogonal components, one component will along this direction, another component will along this direction, and if we decompose this electric field, one component will be minus y-axis along minus y-axis, another will be plus z-axis. So now these two horizontal components will cancel out each other, so net electric field will be upward direction. Net electric field will be upward direction. Now since this plane is symmetric and this is carrying a uniform charge density, so actually we can construct this type of plane by placing large number of infinitely charged carrying wire like this, wire like this. So if we consider another wire here, so exactly we can consider also another wire here. So you can see both the wire, they will create a same magnitude of electric field here, and if we decompose them, then the net electric field will be upward direction. So in this way we can actually say that because of the whole plane, the net electric field at point P will be upward direction. Will be upward direction. Now this is not only true for only this point. This P point we can consider at any point above this plane, because we can shift this origin at any point on this plane, because this plane is infinite itself. This plane is infinite itself. So this P point not only here, we can consider at any point above this plane. So that means every point above the plane, electric field will be upward direction if this plane is carrying positive charge. Positive charge. And similar way, if we consider a point negative z-axis, let's say at this point, let's say point is Q, and if we calculate the electric field because of these two wire, these two electric field will be along this direction, and because of this wire, this electric field will be along this direction. Again, their magnitude will be same, and if we decompose these two electric field, one component will be along this direction, another component along this negative z direction. And if we decompose this electric field, one component will be plus y axis and another component will be minus z axis. So now this y component will cancel out each other, so only we will get minus z direction. Okay, so again, similar way as we have noticed for P, so Q point will also electric field will be always downward if this plane is carrying a positive charge density. And again, this is not only true for this point, this Q point we can consider anywhere below this plane. Below this plane, so everywhere electric field will be downward. Everywhere electric field will be downward. So other way we can say, if we have a infinitely charged carrying plane which is carrying a uniform charge density, then electric field above the plane and below the plane will be always perpendicular to its plane. Perpendicular to its plane. Either it will be away from the plane or it will be towards the plane. It depends upon the nature of the charge. So in this case, if it is positive charge, then above the plane, since it is positive charge, so it will be away from the plane and it will be normal to the plane, so upward direction. And below the plane, it will also be away from the plane, so it will be downward direction. But if this plane carries a negative surface charge density, then also electric field will be perpendicular to the plane, but it will be towards the plane. Towards the plane. For positive charge, it will be away from the plane, but it will be perpendicular to the plane. If this there is a negative surface charge density, then electric field still it will be perpendicular to the plane, but in this case it will be towards the plane. It will be towards the plane. Okay, so direction is clear from this plane, from this figure. Now next important point, how we can construct a Gaussian surface for this type of symmetric charge distribution in order to calculate electric field using Gauss law. So for that, let me just draw this plane again. So let's say this is a infinite charge carrying plane. So infinite plane, and this plane is carrying a uniform surface charge density sigma naught. Uniform surface charge density sigma naught. And also let me draw another circular loop whose plane is parallel to this plane. And perpendicular distance of the loop from this plane, let's say z. Let's say z. Okay. So now if we consider 2 points within this loop, let's say one point is here, another point is here. Another point is here. And if we draw a perpendicular line from this point on the loop like this, so what will be this distance? Since this two plane is parallel and their perpendicular distance is z, so if we consider any point within this loop and if we draw a perpendicular from this loop to the plane, on the plane, the perpendicular distance will always remain z. So this distance is also z and this distance is also z. So now if we put two observers, one observer here, another observer here, So what they will observe? They will observe the same charge distribution because this plane is carrying a uniform charge density. So this observer will see at a distance z we have a charge density sigma naught, and this observer will also see at a distance z we have a charge density sigma naught. Sigma naught. Now if we draw a circle like this around this point, and also if we draw another identical circle around this point, since this plane is carrying a uniform charge density, so everywhere on this circle charge density will be same, as well as for this circle also everywhere on this circle charge density will be same. So now if I connect any point on this circle with this observer point, and same way for first observer also, so what we'll see here, since both the circle have same radius, so this distance and this distance will be same. And again, for any arbitrary point, these two observer will see the same charge distribution at a same distance. At a same distance. So that's mean we can say that these two observer will see the same charge distributions at a same distance. So whatever electric field they will measure, the magnitude of this electric field will be same. Magnitude of this electric field will be same. Now this is not only true for these two observer only, this will be also true for if we put n number of observer everywhere on this plane, on this loop, within this loop. Everywhere within this loop. Okay. So that's mean other way we can say because of this charge distribution, the electric field within this loop everywhere will have a same magnitude. Will have a same magnitude. And now if we consider exactly identical circular loop like this, bottom side of this plane at a perpendicular distance z, at a perpendicular distance like z, the similar way as we have noticed here, same way we can also see that if we put n number of observer here, they will also see the same charge distributions at a same distance on this plane. So because of that, the electric field they will measure at every point on this plane, the magnitude of this electric field will also be the same. Also be the same. So that's mean the observer who is sitting at this plane, the observer who is sitting is this plane, they both will measure the same electric field because they will see the same charge distributions at a same distance. At a same distance. But the electric field on this surface will be upward direction if this plane is carrying a positive charge in this direction, and electric directions of this electric field will be downward direction at this looping direction. But in order to calculate a electric field using Gauss law, we need a closed surface. But these two loops are actually open surface. So for a closed surface, what we can do, we can simply connect these two loop like this. To loop like this. So now you will see this whole surface, I mean this top surface and bottom surface, and the way we have connected them, finally they will form a cylinder. Will form a cylinder. Now cylinder is a closed surface, so over this surface we can use Gauss law. Over this surface we can use Gauss law. Now in this case, since electric field above the plane and below the plane, everywhere it will be perpendicular to the plane, so that's mean electric field will be parallel to the axis of the cylinder. Parallel to the axis of the cylinder. So because of that, the flux through this Gaussian surface that we have constructed here, the flux through this curved surface will be always 0. On this surface will be always 0 because the directions of the area vector of this curved surface will be perpendicular to the axis, but electric field will be everywhere will be parallel to the axis. So that's mean electric field and the directions area vector of the curved surface, they will be perpendicular with each other at every point on the curved surface. So because of that, there will be no flux through the curved surface. No flux through the curved surface. So the flux will passes through only through this top surface. Flux will pass through the top surface and bottom surface only. Top surface and bottom surface only. Okay. And as we have noticed here, that electric field on the top surface and bottom surface on this two layer on this two loop, electric field will be constant, as we have already discussed here. So other we can say the electric field on the top surface of the Gaussian surface and bottom surface will be same. Top surface and bottom surface of this Gaussian surface will be same. And if we say that electric field is E, then flux through this surface, so everywhere electric field, magnitude of electric field is constant, and it will be upward direction, and the directions of area vector is also upward direction. So it's a uniform electric field over this loop, and it's a, in this case this is a plane surface, so flux through this loop will be simply flux through the top surface will be E into A. Similar way, flux through the bottom surface will be E into A, and flux through the curved surface will be 0. So total flux through this type of Gaussian surface for this symmetric plane symmetric charge distribution, it will be 2E into A. 2E into A. Hmm? 2E into A. So that will be the total flux. That will be the total flux. Okay, so I think if you know these two important points, what will be the directions of electric field above the plane and below the plane, and how to construct a Gaussian surface for the plane symmetric charge distribution in order to calculate electric field using Gauss law, then I think we can easily calculate electric field for this type of symmetric charge distribution. For this type of symmetric charge distribution. So let's calculate electric field for some cases. Okay. So first calculate electric field due to a infinite thin uniformly charged carrying plane. So we have a thin infinite plane. Let's say this is a thin infinite plane. Thin infinite plane. So what is difference between thick and thin? So let's say you have a notebook. So if you think about single page of this notebook, then it will be a thin surface. But if you consider the whole notebook, so it will have thickness. So in this case, if you take this cross section area as infinite, so assume that this will behave like a thick plane. Okay, so thin plane means a single plane. It will have single surface only, but if it is thick, then it will include some volume also. Just as I have to give you example that one, if you take your notebook, when you think about a single page of this notebook, it will be like a thin surface, but overall notebook will be applied as a thick surface. So in this case, it is a thin surface. And let's say this surface is infinite. The cross section area of this surface is infinite, and charge per unit area, that is surface charge density on this plane, is uniform, and let's say sigma naught. Let's say sigma naught. Now we have to calculate electric field because of this charge distribution, and in this case, since charge distribution has plane symmetric, because this plane is infinite and this charge distribution on this plane is everywhere is uniform, so this charge distribution actually satisfies these two conditions. The charge is distributed over an infinite plane and charge density in this case uniform. So we can say this charge distribution has plane symmetry. Since this charge distribution has plane symmetric, so in this case we can calculate electric field using Gauss law. So in order to calculate electric field using Gauss law, first we have to draw a Gaussian surface, and we have also learned here that we can, for plane symmetric charge distribution, we can actually consider a Gaussian surface like this. So in this case, let me just draw a Gaussian surface like this. Okay, Gaussian surface like this. And then if we consider that the electric field on the top surface and bottom surface is E, and the cross section of the Gaussian surface, let's say A, cross section of this Gaussian surface A, then according to Gauss law, what we can write? We can write the flux through a closed surface, that is E dot ds, closed surface integral is equals to 1 by epsilon naught q enclosed by this closed surface, q enclosed by this closed surface. So in this case, total flux through this Gaussian surface will be flux through the top surface and bottom surface only, and this will be 2e into a, and this is equals to 1 by epsilon naught. Now charge enclosed within this Gaussian surface, that is the charge lies on this circular part only. So what will be the area of the circular part? That is the cross section of the Gaussian surface, that is A, and charge per unit area on this plane is sigma naught. So enclosed charge within the Gaussian surface in this case will be sigma naught into A. Sigma naught into A. Now from both sides we can cancel out A. So what will get? E is equals to sigma naught by 2 epsilon naught. Sigma naught by 2 epsilon naught. Okay. So this is the electric field, magnitude of electric field. So you see, we have considered this top surface and bottom surface at a distance z equals to, at a distance z, but the final electric field is independent of z. So that's mean everywhere electric field will be uniform. Everywhere above the plane and below the plane electric field will be uniform. And what will be the magnitude? Magnitude will be sigma naught divided by 2 epsilon naught if sigma naught is the charge density. And then direction, if it is carrying a positive charge, then above this plane will be upward directions and below the plane it will be downward direction. Okay. So if we consider this is n cap, then this will be minus n cap. So we can write plus minus n cap here, where n cap is the unit normal to the plane. Unit normal to the plane. Okay. So this will be the electric field because of this thin charge carrying plane. Because of this thin charge carrying infinite plane. Okay. And let's say give a specific example. Let's say this is xy plane, and let's say this plane at z equals to 0 plane. Z equals to 0 plane. So if this z equals to 0, then above this plane z will be z greater than 0, and below this side z will be z less than 0. So in this case, z greater than 0, in this side electric field will be sigma by 2 epsilon naught. And what will be the direction? Since z equals to 0, that's the xy plane. So what will be the normal to the xy plane? It will be plus k cap or plus z cap. So in this case, if we consider like this is z plane, z equals to 0 plane, then above the plane, if this plane is carrying a sigma naught charge density, so what we'll see? We'll see electric field E is equals to will be sigma naught divided by 2 epsilon naught. It will be plus z cap for z greater than 0, and again this will be sigma naught divided by 2 epsilon naught, but the directions now it will be minus z cap for z equals to minus z less than 0. Z less than 0, that is bottom side of this plane. But everywhere you see the magnitude will be same. Magnitude will be same. So if we want to represent this electric field variation graphically with respect to z, then we can see this is electric field on the y-axis, and on the x-axis, let's say perpendicular distance point from the plane. So in this case, just right side this plane, electric field will be sigma by 2 epsilon naught plus z cap, and it will be same everywhere. It will not depends on the z, so same. And bottom side of this layer, when z is negative, on this side also electric field will be uniform. Only because of direction, if we have to draw like this way. Okay, this plus z cap and this is minus z cap. So now, if we know the electric field because of a single plane, single thin plane, so sometimes in different exam you will see this type of questions where instead of single plane, sometimes the examiner will give you more than say 2 plane or 3 plane or 4 plane, and they can carry a same charge distribution or maybe different charge distribution. So let's solve one example like this. So let's assume here at least let's say 2 plane. So these are two infinite plane. And assume that both the plane are actually, let's say, parallel to the xy plane. So this is x-axis, this is y-axis, and this is z-axis. Okay, this is z-axis, and let's say first plane at z equals to 0, and second plane, let's say z equals to a. Okay, where a is some positive value. And let's say first plane is carrying a surface charge density minus sigma naught, and second plane is carrying a charge density plus sigma naught. Carrying a plus sigma naught plus sigma naught. Then examiner may ask you what will be the electric field between at any point between these two planes. Since these are infinite planes, so anywhere if we calculate electric field, everywhere electric field will be same inside this two plane. And or they may ask what will be the electric field in this region, that is right side of the second plane or left side of the first plane. Yeah. Left side of the first plane. So in this case, what we have to do, if we have a this type of more than one infinitely charge carrying plane, what we have to do, we have to calculate electric field due to individual plane first with direction, individual plane direction. And then what you can do, you can according to superposition principle, since we have more than two planes, what we have to do, we have to add electric field of individual plane. So at a times you can consider like this, at a times you have only one single plane. So let's say we want to calculate electric field at this point, between these two plane, between these two layer, consider any point P point. So we want to calculate electric field at this point. So what we can consider, we can assume like this way. So there is only one plane, let's say z equals to 0 plane. Then the electric field at this point will be, let's say, E1. And what will be the value of E1? First write the magnitude. So in this case, charge density is minus sigma naught, but we'll write only magnitude. So what we'll write here, we'll see that magnitude is sigma naught. So sigma naught divided by 2 epsilon naught, that will be the magnitude of this electric field. Now since this charge is carrying this plane is carrying negative charge density, so as we have noticed here, if this plane is carrying positive charge density, then electric field will be always away from the plane. If this plane is negative charge density, then it will be perpendicular to the plane, but it will be towards the plane. So in this case, this plane is carrying a negative surface charge density, so electric field will be towards the plane, so in this direction. So what will be this direction? If this is the positive z-axis, then with respect to this point, it will be minus z cap direction. So this is minus z cap direction. Okay, and then consider only second plane. So assume that there have only second plane, then what will be the electric field at this point? Let's say that electric field will be E2. That electric field will be E2. Now what will be the magnitude of this electric field? So this plane is also carrying a surface charge density sigma naught. So magnitude will be sigma naught divided by 2 epsilon naught. And then what will be the directions? Now this charge is playing a positive charge density, so it will be perpendicular to the plane and away from the normal. So in this case, away from the normal means along this direction. Away from the plane, away from the plane, planes mean along this direction. So it will be perpendicular to the plane and away from the plane, it will be along this direction. So this will be also minus z cap direction. Z cap direction. So now we have two plane and we have calculated electric field because of this individual plane E1 and E2. So if we want to calculate net electric field, then what we have to do, according to superposition principle, we have to take the vector sum of this two electric field, E1 plus E2. E1 plus E2. And if we take the vector sum, then what we'll get? We'll get here both the electric field in the same direction. So we'll get sigma naught divided by epsilon naught, and directions will be minus z cap direction. So net electric field will be along this direction. net electric field will be along this direction, and it will be sigma by 2 epsilon naught, sigma by epsilon naught. Okay, so similar way we can also calculate electric field at this point. At this point, so for this again we'll first consider calculate electric field due to individual plane. So if we say electric field because of first plane is E1, then what will be the value of E1 at this point? So again it will be, see, this plane is carrying a sigma naught minus sigma naught, but we'll write magnitude, so we'll take sigma naught divided by 2 epsilon naught, that will be the magnitude. And direction, since this is carrying a negative charge density, so it will be towards the plane. So in this case electric field will be along this direction, so it will be minus z cap. And for second plane, now second plane, if this electric field is E2, then magnitude again for second plane also be sigma by 2 epsilon naught. But since this plane is carrying positive charge density, so the electric field at this point will be perpendicular to the plane and it will be away from the normal, so it will be along this direction. So what is this direction? This is positive z cap direction, so you can take plus z cap. So now if we want to calculate the net electric field, then what we have to do? Again we have to take the vector sum of these two electric field, and in this case these two electric field are equal but they are opposite direction to each other, so because of that the net electric field will be 0. So in this case outside the right side of the second surface electric field will be 0. And similar way you can also calculate electric field left side of the first surface. So let's say for the first plane, this electric field at this point is E1. So what will be the magnitude? Magnitude again it will be sigma naught divided by 2 epsilon naught. And then since this plane is carrying a negative charge density, so electric field will be towards the plane. So in this case electric field will be along this direction. So what will be this direction? This will be plus z cap direction. So plus z cap. And for second plane, if this electric field is E2, then this plane is also carrying a surface charge density sigma naught. So sigma naught divided by 2 epsilon naught, that will be the magnitude of electric field. Now direction, since this plane is carrying a positive charge, so it will be away from the plane, and at this point away from the plane will be along this direction. So it will be minus z cap direction. So you can see these two electric field have same magnitude, but their directions is opposite. So net electric field will be, if we take vector sum of these two electric field E1 plus E2, they will give us 0. Okay. So in this side also net electric field will be 0. Okay. So in this way you can calculate, actually if we have a more than one charge carrying infinite parallel plane, so for that you can calculate electric field. For that also you can calculate electric field using the superposition principle. So first you have to calculate electric field due to individual plane, and then you have to take the vector sum. Vector sum. And how you can calculate electric field? For that, first you have to just it doesn't matter if it is carrying a positive charge or negative charge, always you assume that this carries a positive sigma charge density. So because of that you will write the magnitude first, and then depending upon nature of the charge you can write what will be the direction of electric field. For the directions, one thing you have to remember, the electric field will be always perpendicular to the plane. Now if this charge carrying a positive charge density, plane carrying a positive charge density, it will be away from the plane. If this plane carrying a negative charge density, then it will be towards the plane. Okay, it's good. Now next solve another problem. So in this case we have to calculate electric field due to a thick uniformly charged carrying infinite plane. As I earlier give you an example, that if we consider in notebook, if you consider single page, then it will be applied as a thin plane, but overall notebook will be applied as a thick plane. And so thick plane you can consider like this way. If you place one page another on the top of the another page, so it will give you finally a thick page, thick notebook. So when you consider single page, it's a thin, but if you place one above another, so you'll get a thick plane. Thick plane. So other way we can see that this thick plane is constructed by a large number of thin plane, placing one above another. Okay, so let me draw first a thick plane like this, whose cross section area is infinite, and let's say thickness is 2d. Thickness is 2d. Okay, so this is a thick charge carrying infinite plane, but this thickness, let's say 2D. Thickness is 2D, and also consider a mid layer. Let's say this is XY plane and thickness is along Z direction. Z direction. So let's consider this is the mid layer. Let me draw it this way. Okay, so this is the mid layer, that is Z equals to 0 layer. Above this, up to from this layer to this top surface will be Z equals to D, and from this layer to bottom surface will also Z equals to D. Yeah. Or other way you can say, on this surface Z equals to 0, so on the bottom surface Z will be minus D, and on the top surface Z will be plus D. And let's say this since this is a thick, so in this case the charge will be distributed over the volume. So in this case, let's say charge is distributed over its volume, and in this case volume charge density is uniform. So in order to, as I told you earlier, that thick charge carrying plane can be considered as a contracted by a large number of thin charge carrying plane. So if each plane carries a uniform charge density, surface charge density, then the volume charge density over this thick surface will be actually uniform volume charge density. Uniform volume charge density. So in this case, uniform volume charge density, and this charge density, let's say rho equals to rho naught. Rho equals to rho naught. Rho equals to rho naught. And this is the mid layer, Z equals to 0 layer. Z equals to 0 layer. So in this case, you can see, if we consider a Gaussian surface inside and outside, so since inside this Gaussian surface charge distributions, and I mean in this case inside and outside there is no charge, and inside there is a charge. So because of that, the electric field, if we calculate electric field inside this thick plane and outside this thick plane, they will have a different nature. So for that, we have to calculate electric field inside as well as outside. So let's first calculate electric field inside this thick plane. So first write here for inside point. For inside point. Okay, for inside point. So you see, if this thick surface is constructed by a large number of thin surface, thin charge carrying layer, and each layer will create an electric field perpendicular to its plane. So ultimately, because of this thick layer also, electric field will be either perpendicular upward or downward. Upward or downward. So now if we interested to calculate electric field inside this loop, for that what we have to do, we have to consider a Gaussian surface inside this plane. So for that, let me just consider a Gaussian surface like this, whose top surface is at a distance z from this mid layer. So mid layer at z equals to 0, and top surface, let's say at z equals to z, and cross section of this top surface, let's say A. So like this, and the bottom surface of this Gaussian surface is also at a distance minus z, and cross section area is A. Cross section area is A, and this whole Gaussian surface is inside the thick surface. So this cross section area is A, and if this top surface is at z equals to plus z, and this bottom surface is z equals to minus z, then the total length of this Gaussian surface will be 2z. Total length of this Gaussian surface will be 2z, and since each layer will create an electric field perpendicular to its plane, so because of that, in this case also, inside this Gaussian surface, electric field I mean inside this layer, inside this thick charge carrying plane, electric field will be either upward or downward. So because of that, through this Gaussian surface, the flux surface through this curved surface of this Gaussian surface will be zero. So only flux will passes through this top surface and bottom surface. And then because of symmetric, we can say that the electric field on this surface and this surface will be same. And if this electric field is E, then according to Gauss law, we can write E dot ds is equals to 1 by epsilon naught q enclosed. And in this case, E ds, that will give you for top surface E into A, and for bottom surface E into A, and curved surface this will be 0, and this is equals to 1 by epsilon naught, now enclosed charge. So enclosed charge in the sense the charge within this Gaussian surface, that is inside this cylindrical surface. So in this case, length of this cylindrical surface is 2z, and cross section area is A, so that will be the volume of the cylinder, and charge per unit volume is inside this layer, it's actually rho naught, so into rho naught, so that will be the enclosed charge. So now from both sides, if we remove A, and then if we divided this 2 on the right side, then what we'll get? We'll get E is equals to rho naught z divided by epsilon naught, divided by epsilon naught. Okay. So this will be the electric field inside the layer at a distance z from the mid layer, that is z equals to 0 layer. So at the mid layer, z equals to 0, electric field will be 0, and then on the both side, as we increase the z, the electric field will increase. Above the mid layer, electric field will be upward, and below the mid layer, if this plate is carrying a positive charge density, then above the mid layer, electric field will be upward, and below the layer it will be downward. So again we can write here, since we have written this is the z equals to 0 plane, so that's mean it is xy plane. In this case, we can write plus minus n cap will be plus minus z cap. So above the plane plus z cap, below the plane minus z cap. Okay, so that is inside. Now if we want to calculate electric field outside this layer, charge carrying plane, then what will be that electric field? So right here for outside point, for outside point, what we can do, we can consider this top surface and bottom surface outside this layer, outside this layer. So let's increase this length of this Gaussian surface in this way. So now consider a top surface outside this layer, and also at the same distance below this bottom side of this thick layer, consider another circular surface, and from there if we draw a Gaussian surface like this. So now this is our Gaussian surface, but in this case charge lies within this volume only, here to here, here to here. So what will be the length of this portion? This portion length will be 2d, and cross section area, let's say still have A. So since each layer carries a, as I told you earlier, that this thick layer is constructed by a thin layer, and each layer carries a uniform surface charge density, because of we are getting a uniform volume charge density. So now, since each layer carrying a uniform surface charge density, so on this layer everywhere electric field will be constant, and on this layer also electric field will be constant. Okay. So what will be the electric field? Let's say if we assume that electric field on this point is A, so electric field on this surface will also be A, because we have considered this both the surface at the same distance from z equals to 0. And if we consider this is E and E, then according to Gauss law, E dot ds is equals to 1 by epsilon naught q enclosed, and then this E dot ds will give you simply E into A for top surface and E into A for bottom surface, and this is equals to now enclosed charge. So what will be the enclosed charge in this case? So now the length of this cylinder, the portion where charge is actually lies within this Gaussian surface, that is only this portion. So in this case, enclosed charge will be 2d into A, that is the volume over which charge is actually lies within this Gaussian surface. So 2d into A, and then charge per unit volume is rho naught, so into rho naught. So that will be the enclosed charge. And then if we divided A on the right side, and also we added this term, we'll get 2 terms, so 2 will also cancel out. So finally what we'll get here, rho naught d divided by epsilon naught. So that will be the magnitude if we consider this top surface and bottom surface outside the plane. Outside this plane, that's mean outside this layer at any point electric field will be rho naught divided by d. That is uniform, that will be independent of z, that will not depends on the distance from the mid layer. At any point outside this layer, electric field will be again constant, rho naught into d divided by epsilon naught, and above the plane it will be plus z cap, and below the plane it will be minus z cap. So let me write like this way, plus minus z cap. Plus minus z cap. Okay, so now we can see here that electric field inside the layer, it will be depends on the distance from the mid layer, because as we increase the, you can notice here, as you will increase the length of this Gaussian surface within this layer, what will happen, enclosed charge will encroach, enclosed charge will increase, and because of that actually the magnitude of electric field will also increase. But as soon as you will come outside from this charge layer, so now after this surface z equals to d surface, if you increase this length, charge within this Gaussian surface will always remain same. So because of that actually electric field will be uniform outside this charge carrying layer. So as I getting here also, we're getting here uniform charge density outside this layer. So now if we draw the variation of this electric field with respect to z, what we'll see here, let's say this is electric field and z. So at z equals to 0, electric field will be 0. At z equals to 0, electric field will be 0. And then z equals to plus t and minus t. So up to plus z, electric field will increase, and it will be in positive z direction. And then it will be parallel to the z axis, means it will be independent of z. Outside it will be constant. And same way on the other side from the mid layer, z equals to 0 layer, up to minus t it will increase, and then after this z equals to d surface it will be almost constant. Almost, not almost constant, or it will be constant. It will be constant. Okay, so this will be the variations of electric field. So this is z equals to d, and this is z equals to minus t. Okay, so I hope you understood how to calculate electric field for plane symmetric charge distribution. So at least we have solved the 3 problems. One is for a single thin charge carrying infinite plane, and then if we have a more than single plane, 2 plane, or in this case we have considered only 2 plane, but if the examiner give you 3 plane, 4 plane, or n number of plane, I hope you can calculate electric field using the superposition principle. At least you get the idea how to calculate electric field for if we have a more than 1 plane, which is infinite, and it's carrying a uniform surface charge density. Okay, and then you have also get some idea how to calculate electric field for a thick uniformly charged carrying infinite plane, where we have noticed inside the plane electric field will increase from with respect to mid layer as we will increase the thickness, or as we will move upward or downward with respect to mid layer, electric field will increase up to the top layer or bottom layer. But as we will cross the top layer, I mean top surface of this charge distributed plane, then electric field will be uniform, and same way from bottom layer. If you cross this line, then if you come outside this charge carrying plane, then electric field will also be uniform. Okay, so now we have completed the electric field due to symmetric charge distribution. So in next class, what we'll do, we will solve some problem. Okay, so next class will be mainly it will be a tutorial class. So we'll solve different type of problem based on the theory so far we have discussed from the beginning. Hmm? we have we have learned how to calculate electric field due to asymmetric charge distribution using Coulomb's law, and then we have also learned how to calculate electric field using Gauss law for symmetric charge distribution. And meantime also we have learned how to calculate flux for different cases, and we have also learned divergence theorem of Gauss law. So based on this theory, in next class we'll solve few numerical problems. Okay, so thank you for watching and see you in the next video.